Hi, my name is Scott. I'm from the Economics Tutoring Center, and today we're going to be doing an example of oligopoly in game theory. So please make sure to check my notation and language use with your instructor because it may vary. So here's our scenario here. We have two basically players or firms in this game. Jack and Jill are both selling water, and they each have the decision to either sell 40 gallons or 30 gallons. So you can see Jill has that decision, and so does Jack. And then the table here is, sometimes it's called like the payoff matrix or something. It tells you that how much, so in this case, it's the profit that each person gets based on their own decision and the decision of the other firm or the other seller in the market. So, for example, I have it color-coded, so any of the numbers in blue are Jack's profits, any of the numbers in black are Jill's. But the other way you would read this is just because these ones are on top, they correspond with Jack, and these ones are sort of on the left of this diagonal line, they correspond with Jill. So, for example, if Jill sells 30 gallons and Jack sells 40 gallons, then this is the result, and we would say that Jill gets a profit of $1,500, we're just going to assume these are dollars, and Jack gets a profit of $2,000. So the questions we usually want to ask with a problem like this are, first of all, are there any dominant strategies for each player, and is there an equilibrium, a Nash equilibrium we call it. So we'll start with dominant strategies for Jill, and a dominant strategy is something that the firm or player play no matter what the other firm does. So for example, let's say, so we're looking at from Jill's perspective. Let's say Jack was going to produce 40 gallons of water, or sell 40 gallons. What would Jill want to do? Well, she could either sell 40 gallons and get a profit of $1,600, or 30 gallons and get a profit of $1,500. So Jill, assuming she wants to maximize profit, will sell 40 gallons and earn $1,600 profit. So I'm going to just put a star to say that this is Jill's best response if Jack sells 40 gallons. So now, still looking at Jill, we say, okay, well, what if Jack instead decides to sell 30 gallons? Well, then Jill could either sell 40 gallons and make a profit of $2,000, or she could sell 30 gallons and make $1,800. So again, she actually gets the higher profit by selling 40 gallons and getting the $2,000 profit. So you'll notice that no matter what Jack does, it's best for Jill to sell 40 gallons because either way she makes more profit that way. So 40 gallons is a dominant strategy for Jill. We could also say that selling 30 gallons is a dominated strategy. It's just never a best response. She should never sell 30 gallons if she's trying to maximize her profits. So we're looking at it now from Jack's perspective. We say, okay, let's say Jill is going to sell 40 gallons. Then Jack could sell 40 and get $1,600 profit, or Jack could sell 30 and get $1,500. So 40 gallons is a better response for Jack. So I'll put the star next to it. And now we say, well, what if instead Jill wants to sell 30 gallons? Now, if Jack's reasonable, he would probably assume, if he knows all this information, he would assume that Jill won't do this. But either way, if Jill decides to sell 30 gallons, it's still better for Jack to sell 40. As you can see, he gets $2,000 if he sells 40 versus $1,800 if he sells 30. So again, we see that it's always a best response for Jack to sell 40 gallons. So that's why we say that Um, 40 gallons is a dominant strategy for Jack. So let's see. Now the last question I wanted to address was, is there an equilibrium to this game? And the common form of equilibrium you see in game theory is what's called a Nash equilibrium. And in words it means basically each strategy is a best response to the other player's strategy. In the case where each player has a dominant strategy, then the Nash equilibrium is always where each player plays their dominant strategy. So in this example, it would be Jill sells 40 gallons, Jack sells 40 gallons. And be careful with your language use here. You don't say that this is the Nash equilibrium. You don't say 1600 is the Nash equilibrium. You say those are the payoffs from the Nash equilibrium. The Nash equilibrium itself is Jill sells 40 gallons, Jack sells 40 gallons. So the reason you can look at the other three combinations of strategies, and we can show why they're not Nash equilibria. So, for example, if you look at, let's say Jill sells 30 gallons and Jack sells 40, this isn't a Nash equilibrium because you can see that Jill could change her strategy to selling 40 gallons and she'd be better off. So if any player can ever change their strategy and become better off, that's not a Nash equilibrium. So, that's not a Nash equilibrium. Same thing it's symmetric, so we know that Jill doing 40 gallons and Jack doing 30 gallons is not a Nash equilibrium. You can see that because Jack could change his strategy to 40 gallons and make a higher profit. And similarly, each selling 30 gallons is not a Nash equilibrium because you can look at it either way. Either Jill could change to 40 gallons and make a higher profit, or Jack could do the same. So that's not a Nash equilibrium. This is the only Nash equilibrium. You can have a game like this one with two Nash equilibria, but in this case, we just have one, and that's because each player has one dominant strategy. So that's the Nash equilibrium. That's all we have today about oligopolies and the game theory behind it. So if you have any further questions, ask your professor or come to the Economics Tutoring Center.